Hello, this is Mark Unkefer. I'm Executive Director of the Fiber Optic Sensing Association, and welcome to this April webinar on the last day of April, the integration of unmanned aerial vehicles, sometimes known as drone, with DAS technology, often known as fiber optic sensing. This is a great opportunity to see how these two technologies work together, and it's always kind of important to understand that those of us supporting fiber optic sensing see it as a component of a suite of technologies dealing with a variety of different use cases. So we're able to hear a kind of great opportunity to learn more about this integration with Stuart Large of Fotech and Matteo Baronio of Cybrid Thrust. So gentlemen, we look forward to hearing your presentation.
Thank you very much. Yes, so I'm Stuart Large. I'm Product Line Director at Fotech, and I'm going to be co-presenting with Matteo Baronio, who's CEO at Cybrid Thrust. And we're very delighted to bring forward this webinar today, and we're going to cover hopefully some interesting topics. So if I may start with the first slide, please. A little bit of background on Fotech, first of all. We were established in 2008 as a spin-out from Surrey University here in the UK to develop distributed acoustic sensing. And we've forged a strong market in the energy, security and transport markets. We combine talent from across the globe. We have an international workforce and operate in a number of countries now. And we are combining leading edge industrial photonics in our DAS sensor, along with technology expertise, which includes software and expertise in the applications of this technology. Next slide, please. Recently, Fotech has been in the news. We're very pleased to be able to say that at the end of December, we were acquired by BP Launchpad. So Launchpad is a wholly owned subsidiary of BP, which operates outside of the main BP organization, because the focus here is to develop and target BP's future in digital, in energy transition, and in transportation, smart cities, and renewables. And for us, it's a very exciting place to be. We're able to now invest significantly in our technology development and to expand our team and carry this business forward. So if I can go to the next slide, please. So let's jump straight into giving a bit of an idea of what we're looking to do with our technology. This example is from a pipeline which Fotech systems monitor in South America. And it so happens that actually while we're doing a site acceptance test, so very early on with the implementation of our system there, as we were monitoring the pipeline, we noticed some vibrations in the ground near the pipeline. And we highlighted these to the client as something to be concerned about, something requiring investigation. And at first they were perhaps a little concerned because they said, well, this area of pipeline is so far in the rainforest that we just don't expect anybody to be there. But we were quite convinced that these vibrations we were detecting had to be caused by people, wasn't naturally occurring. So we insisted that a vehicle was sent out there and this situation was investigated. And when they got there, they were surprised to find a mining exploration crew at work, drilling holes in the ground in the pipeline corridor. And their plan was to put explosives in those holes. And as part of their seismic survey, to detonate those explosives and record the seismic response. Well, had they done that, they most likely would have actually blown up this gas pipeline, doing immense amounts of damage and quite possibly serious harm to themselves, possibly fatalities. So we were lucky here, but also, of course, it's the fact the system was there that we were able to respond and prevent this serious accident. But let's make a note, time was critical. And actually, in some ways we were lucky, because of course it takes time to drive that vehicle out there and to reach site and to stop the activities. What we're going to show you today is that there's a faster way to respond. So the next slide, please. Now, in actual fact, response time is nearly always critical. It can make the difference. If it's a pipeline, it could be to stop somebody hot tapping the pipeline or causing a major leak before it actually becomes serious. If it's a cable, whether that be onshore, where perhaps there's an attempt at theft, or whether it be subsea, where maybe the cable could be struck by a vessel. In each case, response to that activity is critical. Obviously, a perimeter or border, we want to be able to respond quickly to be able to catch those with ill intent. Or on a road or a railway where we detect an incident, perhaps an accident or rock fall onto a railway line, we need to be able to verify that incident quickly and carry out the necessary action, which in a case of a rail could mean actually stopping trains. So next slide, please. Now, I know many of you on this call are familiar with distributed acoustic sensing, but there's probably a few new faces on here too. So let's just quickly run over that. We're using a standard optical fiber, as brings the internet to your home or business. So I'm effectively communicating with you through one of those fibers now. But what we do is connect our DAS interrogator to one end of the fiber, and we send pulses of light down it, many thousands of pulses a second, and the fiber could be a few tens of kilometers long. And then we are looking at the light that is reflected back. That's through the process of Rayleigh backscatter. Now, if there are sounds or vibrations around the fiber, they will actually interfere with the light that is traveling in the fiber. And that is what we're interested in detecting. So in effect, we're able to turn that fiber into a series of thousands of microphones or vibrational sensors. So if you think about a case of a pipeline, if somebody approaches that pipe to try to hot tap it, we will detect their footsteps, and then we'll detect digging in the ground, and then perhaps tampering with the pipeline. All of these things are sensed by that optical fiber. And the real clever bit, of course, is the software, which is able to run in real time algorithms on the data to recognize the particular signatures of the events we're worried about and to generate alarms at the right time, but also to eliminate the other disturbances which are not of concern. Next slide, please. So what we've done, because of course an installation may involve multiple systems, some of our pipelines are 1,000 kilometers long. So we have a modular system where we have the DAS interrogators, which we call Helios, and the Panoptes alarm servers deployed into modular racks, which can then be easily rolled out and installed at the suitable locations along the length of whatever asset it is, a pipeline or a border. Next slide, please. And then we have the alarm system, which is part of that module. And this is the point at which we start to interface with the UAV system. So as events are reported to the alarm module, maybe we detect some digging near our pipeline. Well, at first, it will be noted as a green level alert. But then if it persists over time and over a number of digs, it will be elevated through the levels of an amber and ultimately a red level alert. And dependent upon the thresholds that we've set, we'll be choosing the time at which we need to respond. Usually that's a red level alert. So at that point, a message will be sent to the UAV system with coordinates and times and the nature of the activity so that the UAV can respond. And it's at this point I'm going to hand over to Matteo to take us from here.
Thank you, Stuart. So I'm Matteo Baronio, CEO of Cybrid Thrust, and I will present you the part related to the UAV. So as we understood from the presentation of Stuart, the UAV is a logic integrated terminal step in the security cycle of the infrastructure. And of course, in a wider context, its introduction in industrial processes and what we call today the Industry 4.0 is becoming more and more sophisticated and creating unique value from various perspectives for the data collection and optimizations of the workflow, for example. And of course, this is the case for the protection of critical infrastructure. Next slide, please. So some of the benefits of the integration of a UAV in this context are listed here. And of course, the faster response time is the first that we think about it in terms of benefit. We can say also as being first operator on site then, rather than first person on site, we prevent any risk to the security team that would eventually be deployed in a place where a crime is being committed or any other threat to the infrastructure is being carried by a criminal organization. So another benefit of the use of UAV, because of the improvement in carrying loads under them, is of course to carry some kind of effectors that will allow the UAV to assess and engage the threat before the human responders arrive. For example, interacting with loudspeakers, spotlights, and other effectors, to eventually dissuade and interact with the threat. So the ability to assess and engage the threat is what will ultimately make the change in the way at the moment those type of incidents are handled, because of the long response time that can occur before being on site. Another important point is the deterrence that is provided by operating those UAV, in the sense that those UAV can be operated above the critical infrastructure, not only based on the response of an alert of the Panoptes system, but also to have a deterrent effect by their presence and flying above the infrastructure. Another point that is important is that the payloads that can be under the drone, for sure, payload like infrared cameras or daylight cameras, will allow, in the case of a criminal investigation, to acquire evidence of the theft or the hostile activity. And of course, in the case of further engagement with those criminal actors, we will be able, with those payloads, to track and follow the intruders after discovery of the harm that was being done to the infrastructure. Another important point is the support the UAV will bring to other activities related to the asset. For example, for what we call the digitalization of the asset. And we will see that for some inspection purposes, this UAV will be also useful for other application around the infrastructure. Next slide, please. So I will just give a brief word about Cybrid Thrust. So I'm the CEO and founder of the company, and we established the company to enhance the Industry 4.0 and the security and defense markets. So we develop and advise on turnkey solutions centered on robotics and related cutting-edge technologies. So we approach this, what we call now cyber physical systems, both with the mind of an engineer and the heart of a security professional. And this is very important because we will see that those new technologies interrelate very often also with some security aspects. Next slide, please. So what is really critical in selecting the proper UAV technology for this type of application is, of course, the knowledge of the state of the art in the industry. So UAVs are fast-growing technologies and a concentration of technology by themselves in terms of materials that are used to build the birds, as I like to call them, but also for the data links that are used to pilot them, the type of energy and the weight of the payload. So there are more and more sensors and new applications that are allowed through the use of UAVs. So one point that is very important is the identification of the scenario-based requirements. We will not operate the same type of UAV in one context like confined space inspections like we will do for an application that will require long endurance to withstand weather condition and the ability to adapt, for example, to the speed of a tracked vehicle. This, for example, it will be much more difficult with a fixed wing UAV as well as hovering above the threat. Another thing we will definitely look into is the reliability of the platform. And in such critical context, the return of experience of similar mission or similar industry, like the Formula One and automotive, will indicate that some components needs to be carefully chosen to ensure this reliability. What is important to mention is in these categories of UAV, so we are talking here not about the male with long endurance UAV that we are familiar from the world of the security and defense industry, but the more, let's say, smaller UAV that fly at a lower height. Much of them come from, let's say, a more hobbyist and do-it-yourself approach. And this cannot be when we are considering the securization of a critical infrastructure. So what is important to know is some other industries, like the automotive industry, have much more, let's say, return on experience on the type of components used and the type of autopilot used. And these type of things we should capitalize on them to build and select the UAV of the future for this type of application. And the open and flexible architecture of those components is what will ensure that they can be interfaced with other systems and in a system of systems, actually. With some type of, let's say, mainstream commercial UAV, of course, this will not be possible. And this same open and flexible architecture is what will allow the integration of a wide range of professional payloads, either for tracking, detecting hostile threats, but also to carry powerful inspections with sensor like LiDARs and other type of sensor, high-end sensor to carry inspection of the infrastructure. So the piloting part is also very important for this type of missions that we would qualify as a critical mission. We need to have a very reliable and user-friendly human-machine interface to be able to allow the operators not to get more complexity in their day-to-day job. And last but not least, the service and maintenance would be also a point of attention in the selection of the UAV technology, because such type of investments are made, of course, to last. And if we don't use a proper service and maintenance framework to have in real time the status of health of the UAV, depending on the mission that he carried, it will be problematic. Next slide, please. So in this slide, I think we will have a little introduction and video about the operation of such a drone. So there will be a little transition of screen at the moment. And as soon as the video is launched, we will be able to see in real life how this type of UAV operates in this context of inspection and securization of critical infrastructure. So I don't know if we can launch our video. A little patience before we are almost ready with it. So here we are back from our video interlude. So if we can move to the next slide, we will talk about these UAV specification and how are they relevant for the case of pipeline securization, for example. So as you have seen, the UAV we presented here is not a multicopter, neither a fixed wing UAV. It's actually a helicopter. And this is important in the sense that it differentiates from, for example, fixed wing by its ability to take off and land vertically, what we call a VTOL UAV. At the same time, we have the flexibility to land at any place, and in case of unforeseen situation, we can land on the spot. while this would be much more difficult to reach with fixed wing, of course, that needs either a catapult to take off, or a parachute to land with quite some uncertainty around it. So this particular model is using the Jet A fuel. So it's very safe to operate rather than other type of carburants. It has unprecedented speed and range compared to the same UAV of this category. What's important to know is we are here staying in a UAV category that is not the one of the same type of UAV we use in the military. So it's still below 150 kilograms. So it's completely suitable for what we call commercial operation. At the same time, it ensures an optimization of the use of this carburant to allow long flights and long range flights at high speeds. And it is powered by proprietary autopilot, allowing fully flexibility in terms of payload integration, like the payload we have seen here, which is for ESR, so intelligence surveillance and recognition, very suitable for spotting intruders in a perimeter, for example. We can move to the next slide. And we will talk about the integration of the technologies on the UAV. So next slide, please. So when we consider this UAV, what is really important is all the aspects related to the flight management. So this means to have proper crew and operators trained with well-defined duties and responsibilities. We need to have in place the proper communication, either with a command center or between operators, and to also know what is the difference and specificities of different type of operation, like daylight operation and nightlight operation. So chase flights that are also possible in the type of scenario we are considering also will require some type of skills in terms of piloting. But of course, the goal is to have a maximum of the operation of the UAV done autonomously through a system, the human-machine interface that will allow to fly to a point defined on the map or sent by the Panoptes system. So what we recommend as well is in this type of application where the site is known is to proceed to site surveys in advance, to have a digitalized and what we call a digital twin of the asset to protect, so that we can properly modelize it in the flight management system, so that we have up-to-date environment loaded in the map with the maps of the region. Of course, the system and the management of the flight will ensure that all pre and post-flight checks are carried to ensure always secure operation of the system. And we will retrieve every time the logs of the operated mission in order to know, for example, how many hours the UAV has operated in one or another context. Next slide, please. So in this next slide, we give an overview of what would be the glass cockpit, as we call it, with the various flight parameters. What is really important to know is that the autopilot is proprietary. So this means that it's not an open source available autopilot, mainstream autopilot. So it's completely, we have complete flexibility on how those various tools are displayed, and we can eventually modify the glass cockpit just to show what is the necessary information during the mission. I want to draw attention on one particular point that we can see from the map, is that we can draw the waypoints in 3 dimensions. So we can establish 3-dimensional waypoints, which is quite powerful to some type of operations in a very scattered landscape, let's say. And of course, all the other usual flight parameters are displayed, like the asset, the balance of the UAV, as well as all the parameters that are specific to the payload that is carried, and which will eventually need some adaptation depending on the condition in which the flight is operated. We can move to the next slide. So one important point I will touch on is the UAV maintenance and refueling. So here we use and we inherited, let's say, the maintenance software from bigger aerospace companies to keep it as professional as possible, and this allows to use what we call cloud-based advanced asset management. So this is based on Airbus Helicopter Continuous Airworthiness Maintenance Organization Program, what we call CAMO, and it allows for each piece, each component of the UAV to know how much time it operated, in which condition, was it in rainy weather, was it in sandy weather. So all those information are stored and logged for each UAV and each subcomponent to have a up-to-date status of the UAV. And yes, some particularities about the type of fuel used I mentioned already. So we can use Jet A1 aviation turbine fuel, and it is EASA compliant. So it's important to comply with regulation when it comes to standards of airworthiness, and the machine is completely suitable and compliant in that regard. So this is the end of my presentation of this UAV. I will just present very quickly some other example in the last 2 slides about what we can do on top of the surveillance in terms of inspection with other type of payload. For example, integrating what we call high definition cameras. So we have in this way a possibility to map and to identify with a sub-millimeter accuracy some deviation in the images that are also interesting to identify some particular facts, like here this drainage pipe. And next slide. So in this one, we see what we could do by, for example, by integrating LiDAR technology and modelizing the asset in a digital manner, or with a thermal camera to identify hotspot along the infrastructure. So those are other benefits, as we mentioned, that come with the use of the UAV in this context. And that's all for my side for the UAV technology. So I hand the floor again to Stuart, so we can know more about integrating those technologies to protect pipelines.
Thank you very much, Matteo. So for my last part, I would like to just review a few practical examples of how we can now deploy this technology for our different applications. So if I can move on, actually we can advance a couple of slides. Thank you very much. So this is an example from India, where one of our systems is monitoring a 72-kilometer stretch of pipeline and high levels of activity here. We have detected 26 hot tapping attempts in just 6 months. And in the photo there, you see the typical scene where a hole has been dug by hand in an attempt to get down to the pipeline and hot tap it. Now on this pipeline, there are line walkers employed to walk up and down. Of course, the people digging the hole can just keep an eye out and see when the walker is coming even a few kilometers before they arrive if they've got people in the right place, and know when to move away and not get caught. Or if the security team comes, they probably see the headlights from the Jeep approaching and run off into the woods. Sometimes they are caught, which is the good news. But let's look at how we could respond with a UAV. If we go to the next slide, please. So now if we're thinking about response time, what we're going to consider here is how many UAVs do we need to cover a pipeline? How can we space them out to get the level of response that we need? Now, I think we need to look at it from two sides. One is, how long would it take the criminals to get down to the pipeline and to fit their tap on it? So of course they need time to dig, and the time to dig is affected by how deeply buried the pipeline is, what the soil conditions are like, and also what method of digging they're going to use. In some places you could perhaps get machinery onto location, but in others, such as here, you wouldn't do that. So that sets a certain time. What you don't want to do is to arrive partway through the hot tapping, have the guys run off, and then leave you with a leaking pipeline. That's when things get really quite messy and potentially expensive. Now look at it from the other side, is how quickly can we fly that UAV? Well, we need some time, but not much time, a minute or two, usually, to raise an alarm, so to detect the walking or the digging, whatever we're looking for, and to transmit that to the flight management system. Maybe a few seconds for the UAV to be launched and then set on its way. And then you've got the velocity of the flight, so simply how fast can it fly to get there. And also, of course, you have to consider the range and how long the UAV can stay in the air when it gets there, because you don't want to have to turn back straight away. You might want to continue to follow people for a little while if you discover them on site. So let's just work through a little example on the next slide, please. So typical example, pipeline buried about 2 meters deep, typical soil, let's say, with some clay content, and we're going to have to dig it by spade. So you might estimate it's going to take around 45 minutes to dig down to the pipeline. So that sets the maximum allowable response time. Now look at it from the other side, the time to detect that digging, raise an alarm, launch the UAV. We could probably do it in less, but let's say 5 minutes to be conservative. And then if our UAV, such as the one shown in the video here, can fly at 90 kilometers an hour, well, then we can cover 60 kilometers in the remaining 40 minutes. So that sets the spacing that would be allowed between stations of the UAV. Now, of course, on a pipeline, from one point, it could fly in two directions. So from one station, you can cover 120 kilometers. If we give ourselves a safety factor, it might be reasonable to say 100 kilometer spacing is reasonable. That would just give us a bit more of a buffer on the time, but also allows us situations such as where we may have to fly against the wind in order to reach location. But as you can see, that 100 kilometer spacing fits quite well with what is typical for the implementation of DAS-based systems along a pipeline or along a border. So next slide, please. Now let's consider another application, looking at offshore wind. Clearly we have a number of cables. There's the interconnectors linking each of the wind turbines, and then there are the export cables that come to shore. All of these can be monitored with DAS systems. Now, a number of threats exist for these cables, and repair of when there's a failure is expensive. To get a vessel out there usually costs a few millions of dollars, and also you have significant lost productivity. And particularly when these cables are struck by a vessel, either from dropping an anchor or dragging a trawler net across the cable, that's something we'd really like to prevent. So if we go to the next slide, please. So here's just a little graphic of that anchor drag situation. So in this case, we would expect to hear the impact of the anchor landing on the seabed, a big vibration detected by DAS, and then the activity of the anchor being pulled through the seabed and then snagging on the cable. Next slide, please. Now, with the DAS, we will have a spatial calibration, so we'll know where on the map the affected area of the cable is located, and we can correlate that with shipping data. There's publicly available AIS data out there with which we could detect and determine which particular vessel it is that we think is deploying that anchor or fishing net down to the seabed and hitting the cable. And then on the next slide, one way to respond to this, and certainly in a timely manner, and to collect the evidence you potentially need if you may wish to prosecute, is to actually go out and video or photograph that vessel and gain the evidence that shows it with its anchor over the side or the nets deployed. So we've got a complete package there to detect and respond and collect our evidence in the most timely manner in this particular case. On to the next one, please. So a few more scenarios. Obviously, borders, it's quite a hot topic these days, and an area in which distributed acoustic sensing certainly plays a role. Rather like a pipeline, we expect to see systems deployed at intervals with fibers monitoring in both directions. And here we can likewise place UAVs at each of the modules and patrol in different directions up and down the border. And again, to one of the points that Matteo made, it's not just about launching and flying to a location that the DAS provides, but also there'll be some level of deterrence and patrolling in between times. But it just means that with DAS, we can be far more focused about where we fly the UAV to make sure we stand the best chance of intercepting and picking up on activity. So next slide, please. Now on this next one, we're considering a situation of a perimeter. This could be around a nuclear power facility or a military installation or government installation, anything really. But the model here would be to have a UAV located somewhere in the middle, and that would be able to fly out to the location of disturbances that are detected by the DAS system. And next one, please. This next scenario we refer to as corridor security. So it could be different things in this corridor. It could apply to a railway line where we're worried about intrusions from either side, where there are fences on each side of that railway. Or it could be a pipeline corridor. Sometimes it's not really feasible to monitor every single pipeline. There could be 10 pipelines running parallel, and actually the most efficient way to protect is to have a fiber laid on each side of the corridor, detect intrusions, and then send a UAV out to the location to see what is happening within that corridor space. Again, we can locate those UAVs at the same locations as the DAS systems and launch from there. To the next one, please. So just coming back to pipelines, obviously what we've tended to talk about so far has been intrusions, but there's also the concern with leaks, of course. So, particularly over recent years, it's been recognized the role that distributed acoustic sensing can play in detecting leaks and to give a very quick detection of a leak where other systems may actually take a good few hours. But also, if we launch the UAV, then we've got opportunity to get some further eyes on the ground, so to speak, to see if there's any evidence at ground level of a leak. Maybe even have a sensor package on board that could detect maybe the presence of gases or oil vapors in the air. And also it could be used to drive people or animals away from potential danger. by kind of buzzing the area, if you like, or to use lights and audio signals to warn them away. And there is technology now emerging to perhaps carry a first spill kit to help control the leak in some way. So there's a number of ways in which the UAV could prove very useful here. So the last slide then, if I may wrap up. Why combine distributed acoustic sensing and UAVs? Well, we believe that with DAS, you have the tool with which to detect specific threats and distinguish those from the complex background noises, and to provide a precise location of where there is a threat to your asset. A clear, high confidence alarm will be raised, which gives you, again, that conveys that precise location, time, and some information about the nature of the threat. But then in the UAV, you've got the best possible way to respond. Something that is fast, it's safe, so it keeps people, a security team in particular, away from harm, because they don't have to be the first responder anymore, walking into the unknown, but rather they've got the bird's eye view that comes from the UAV, and that first assessment of whether the people they're going to be dealing with are perhaps armed, and how many there are, and what vehicles they might have. And then also, if those people start to run, then of course, from the air, particularly from a helicopter kind of design of UAV, we're able to track those people and make it very difficult for them to escape the long reach of the law. So there we are. To conclude, we can react quickly, we can provide deterrence, and we can help operators preserve their reputation by responding in the right way and dealing with threats to their assets. Ultimately, of course, that saves money and drives efficiency. And with that, I say thank you very much. And last slide is really just to say thank you and to invite questions from the audience.
Thank you very much, Stuart and Matteo. To ask a question, you can put in your question into the text box that's on the right on your screen. I do have some questions already, but basically this is directed at both of you to get a better sense of what the ranges are, both for sensing, Stuart, but Matteo, also what the range is for your UAVs.
Okay, well, sensing first of all. Typically we'll say that DAS interrogator can cover up to 50 kilometers in each direction. We have 2-channel systems. Now, of course, the technology continues to evolve, and also, the range depends upon the environment and the applications that we need to be running. But that is typically a reasonably good figure to work with.
On the side of the UAV, we can count up to 100 kilometers of operation. So it fits quite well with the metrics for the DAS, and yeah, so it could we can consider to operate like 50 kilometers on one side and 50 on the other, for example.
Thank you. Matteo, I guess this is more directed at you, which is to get a sense of the flying regulations country by country. What kind of permissions are necessary to operate one of your UAVs?
So this is a huge topic in the sense that we are now facing more and more standardization of the rules. So the standardized rules are developed. It remains a country prerogative to have a proper regulation for the operation. But from what we see is generally we need to have some kind of operating manual for a company that would operate such a system, and a piloting license. Those are generally the two main prerequisite before starting to use the UAV.
And this is a little bit more detailed question on the same point of how many applications with UAVs do you have in the US? Do they require visual line of sight, or have they gotten beyond visual line of sight waivers from the FAA?
So the UAV presented here is fully FAA compliant. It has been actually one of the first UAV that has been operated in the US more than 30 years ago in the movie industry. This is why he's well known in the US. In terms of BVLOS application, I think the US is quite, let's say, open for that type of operation, more than maybe some other places in the world, with the proper risk assessments and demonstration that we took all the safety nets to operate the system in that particular context. I don't see why we would receive a negative, let's say, response from the FAA, knowing that BVLOS and even autonomous operation are already occurring. So,
okay, and how does the UAV avoid obstacles in flight? Is there particular tools that you use for that to avoid
yes.
potential collisions?
Yes, absolutely. So first of all, we need to put the operation here in the context of a known asset where we would know the particular topography of the place. But at the same time, if we would consider an unexpected encounter, we would, of course, mention this in the previously in the aviation risk assessment before the mission, even though some encounters are highly unlikely, like the encounter of a kite. I mean, that's the same that could happen to other type of manned aviation as well, and yeah, we know that is highly unlikely. On the other side, from the sensor point of view, we can include some option to have a forward-looking radar to detect obstacle. So that is the type of thing we could embed in the system. But more importantly, the knowledge of an existing obstacle, like a power line, a bridge, a tower, or a building, is part of the whole system setup. So we generally generate a digital map, what I call the digital twin of the entire area to survey, and that will be the base of the mission planning and flight management.
And so I guess this question is directed at both of you to kind of elaborate on the integration of the matrix of referentials to your system. So you've got GPS, you've got the feedback that is coming from the DFOS system. How does that all work together? Is that done on a common system, or are there other ways in which you integrate that?
So what I know is from the Panoptes system, we can receive the proper indication of the location of the threat and of the alarm detection. And then the UAV concept is based on a command center, which is actually in communication with all the ground control station of each UAV. So those same ground control stations are themselves in control of the various UAV on the area to secure, and can then pass the message to the GCS that is in control of the UAV closer to the point where the alert has been raised.
So just to follow up on that, you can change course or change your target in mid-flight, perhaps as you detect new information that comes from the DAS or some other source.
Yeah, that's actually a very basic feature of any, let's say, piloted robot, if I can call it like that. So we could at any time during the mission just what we call a feature that we call fly to point. So indicate a point on the map, and systematically the UAV will put on hold his mission and fly to the newly identified coordinate.
Now this question's directed at Stuart, and it's really to kind of follow up. I know you used a couple of examples, but I guess they're looking for more specifics about the number of implementations that you've had so far for this sort of combination system.
Well, yeah, so the examples I've shown today are taken from some of our existing implementations where currently there is no UAV. I was really looking at it from the point of view of, how could we respond better where a UAV were deployed. So at the moment, what we're showing you here is new technology, but we've done the work to show exactly how these two systems will work together. DAS has been installed on many systems. These UAVs have flown in many missions. It's relatively straightforward to combine the two.
And here's a more technical question. I guess it goes back to Matteo, is what kind of communication channel do you need, and are there particular frequencies that you operate in?
So that's a very good question. Thank you for this question. So on the side of the data link, we are quite agnostic actually, and we will see that depending on the context, civilian or military, or depending on the regulation, some adaptation needs to be done on the data link to comply with either local regulation or requirements from the end user in terms of frequency. So we are fully flexible on the data link. We can integrate some preferred vendors of the end user. That's what usually happens for the military. And for more civilian application, we have our own, let's say, data link that is suitable for the BVLOS operation, and that we can propose and adapt in terms of frequency and emission power to comply with regulation. So it can be phased array panels, like it can be radio frequency. So we have various mode of operation for the data link.
And here's a follow-up question for that. Are there anti-jamming systems integrated into the UAV? So here's somebody who's thinking ahead of the countermeasures that the bad guys might be using to defeat this system.
That's a topic I'm quite familiar with, as I'm active also in that arena, I would say. And I can say that without disclosing any proprietary information about the manufacturer, some improvement in what we call EMU technology, so positioning technologies, would allow in some critical context for the UAV to be more resilient to this type of interferences. So when we talk about jamming, it's very wide topic. So we would need to know better which type of attack against the UAV we would consider. But the security by design approach is meant to use positioning components that are that can go through this type of hostile attacks.
Well, it sounds like there's almost an arms race in which you're keeping a couple of steps ahead, and that's obviously very encouraging. We're coming up to the hour, so I think I'll cut off the questions. You do, of course, have on that last slide the emails for both Stuart and Matteo. So for sort of additional questions, you can get in touch with them, and I'm sure they'd be very happy to answer that and provide that much more information. This webinar will be posted both on the FOSA website and on our YouTube page, as are all our webinars, and so that's a resource that's going to be available for folks within the 24 hours at the latest. Usually we're able to do it in a couple of hours right after the completion of the webinar, so you can pass that on. And we also have a webinar coming up in May 14th. This one will focus on fiber optic sensing for high and medium voltage power conductor cable, so it's an opportunity to look at the electric transmission use case. So both Stuart and Matteo, thank you very much for what was an extremely informative presentation on how DFOS can be used in the real world. Thank you
Thank
all,
you very much.
and that concludes this webinar.
Thank you.
Thank you. Goodbye.